All right, let's start. So, welcome guys. Thank you for coming. And this is the class about the promise of quantum computing. We know it's a subject that most of you heard about, and this is it. So, we'll talk about what do we want to achieve with this class later on, but today we'll just start with the basics. Okay, so if you don't know me, some of you already know. I'm an MBA student at Sloan. I'm VP at the Tech Lab, and we run the Sloan Quantum Initiative. So this course is part of this initiative to bring quantum technologies in general to a wider audience. My background is in materials engineering. Before coming to Sloan, I worked at Intel for over 6 years, served in the Israeli Defense Forces, married, and this is my son.
All right. So I'm Eric. I have a. Oh, thank you very much. I'm the technical marketing manager for a company called Classic. We're a software development platform for quantum computers. I have a doctor from the University of Rochester in laser physics. Had a fun time shooting high-powered lasers at metals all day. Had a big red button. It's my favorite part of it. I also have a master's in business, specifically in technical entrepreneurship and management. So all kind of the front end of business, starting a business, and once you hit IPO, I have no idea what to do after that, but leave that to other people. Used to be innovation product manager for a company called IP.com and innovation research scientist for Kodak Alaris. So had a lot of fun years there at Kodak, working with them. I'm the father of 2 young girls, and since you put some personal things on yours, I decided to throw some on mine too. I'm a big nerd, and I love the Dungeons and Dragons, and I play the ukulele. All right. So definitely, I'll leave this to you, but one thing we wanted to say in this is that let's not have this be purely lecture, right? If you have questions, if anything you see on the slides intrigues you, ask about it. We'll have a dialogue. It'll be fun, right? We want this to be engaging and kind of a back and forth conversation with everybody. So you're here because you're interested in quantum computing, so ask about quantum computing.
So, kind of like the main goals, we want you to understand why quantum computing, why people are excited about it, why governments and investors spend so much money and pour so much money into this technology. We want you to be able to understand the basics, like why it does what it's supposed to be doing, how it's actually doing it. You will run your first algorithm today, and we'll get it more and more complex. Tomorrow we will use Classic's platform. We'll show you how we can even simplify it and make it even much simpler, like to develop your own applications, your own software, your own everything. And of course, we want you to be able to impress your friends, like quant stuff like that. Some of the slides, which are slightly more technical, we'll either just skim over them or totally skip them because for the sake of time. But if you have questions, stop us. We'll answer to the best of our knowledge. And we hope you will have fun. So today, what we plan to cover is the following. We'll start with the motivation and history, how we got to this idea of quantum computers, how it started at all. Really easy and quick math refresher. Just the things that you won't need to do any kind of calculations at all. We just want you to have the same terminology and understand the language, right? So it's just the basics. From that, we'll transition to quantum mechanics, how we implement this math and how we use it for quantum mechanics, how we express all those ideas that we will talk about. And then we'll start to get into the interesting stuff. We'll compare classical and quantum computers, how they work, how they do stuff, how we handle information, what is similar and what is different, how we actually build quantum computers, how we use them. And after lunch, we'll do the hands-on demo. Right? So you will get your own time. If you didn't set up your IBM client, we'll help you do it. We do everything together, so no stress about it.
Absolutely, and
Kick us off.
oh, definitely. But I want to just tack on one thing. If we don't get through the whole lecture series because the conversation is so engaging, don't worry about it. We'll have the slides available after the class. So, again, feel free to ask. But certainly, one of the things that kind of kicked off certainly the interest for quantum computing was a couple of research papers, right? Most notably, one by Richard Feynman, when you could have some more colorful academic papers. Certainly, you can't get away with this language in academic papers today. But he said, very quotable, is that nature isn't classical, damn it, right? And if you want to make a simulation of nature, you'd better make it quantum mechanical. And for somebody who worked in the Manhattan Project, he would know firsthand, right? Nature doesn't behave classically. Somebody had to do those calculations. If the best way to handle this, the best way to simulate nature is to figure out, how do I simulate it? Well, the best way to simulate nature is quantum mechanically. So we need a quantum computer, some quantum system. At that point, it was all very hypothetical. It was all kind of just a thought, right? Thought exercise. But there's a lot of interesting applications for quantum computing, right? The whole reason that we're here and we're interested in it today are the numerous applications for it, right? There's tremendous applications in healthcare. Right now, drug discovery is all trial and error, right? You have these drugs, you're trying it one at a time, you're seeing, how does this protein interact with the human enzyme? And that's because all of this is quantum mechanical. It's very difficult for computers to simulate these kind of fundamental interactions. So if we can do this with quantum computers, we can have very rapid drug discovery, right? Imagine having the COVID-19 vaccine discovered in, a month or, instead of however long it took. Actually, that was quite rapid, but that's because they had some development already in the pipeline. But still, rapid drug discovery as opposed to just trial and error. Of course, physics research, right? Simulating nature is always going to be a high topic on there. Engineering, right? One that's quite intriguing for even a number of our clients for Classic is computational fluid dynamics, right? Nature doesn't behave classically. A lot of these fundamental interactions are quantum mechanical. And so if you want to simulate it to its truest behavior, you need to simulate it quantum mechanically. And then there's also some interesting applications for optimization, right? You can do cool city planning, right? You can have better stoplight traffic, better UPS directions getting to your house. What's the shortest way to get from point A to point Z or hit all these houses along the way? That's a problem we'll talk about later called the traveling salesman problem. And it's remarkably difficult for a classical computer to solve this, but it happens to be a problem that quantum computers can handle quite easily. All right, so going to go through a timeline of kind of what happened with quantum computing. And quantum interest really started up, or the concept of quantum really kicked off with this double slit experiment. This is kind of the first thing you hear about when you learn about quantum in general. It's kind of your first introduction in high school. What is quantum computing? You have a metal sheet with two slits, right? And you're shooting electrons through them. What you end up seeing is that when you have two slits and you're shooting tons of these electrons, you get a diffraction pattern, right? Okay, so that's explained. People are writing papers. They're bouncing off each other clearly, and so it's causing local minimum and local maximum. Cool. They did it with one slit. They get a single line. Everything's making sense so far. Great. What happened afterwards was they took it to its next logical conclusion, and they shot single electrons at a time. Instead of shooting tons of them, single electrons at a time through two slits. What they found is that it still behaves like a wave pattern. You're still having local minimum and local maximum as if it was bouncing off of other electrons. What that shows you is that electrons fundamentally behave probabilistically. They don't behave classically. The only time they behave classically is when you observe them, right? When they turned the camera to face what was happening. Through the two slits, you got two lines. Turn the observer away, it becomes a diffraction pattern again. And that's kind of, okay, what's going on here? This is new territory, this is very interesting. And there are other bits of the puzzle along the way, black body radiation, kinetics of gas. And then people started to put the early pieces of this together, right? The Bohr atomic model. We're starting to understand how things are coming together a little better, right? Planck's constant, right? Pauli exclusion principle. And it really was until 1925, 1926, so we kind of put it all together. We have Schrodinger, who came out with this great Schrodinger's equation. We'll talk about that later. Very nice and easy way to kind of explain quantum mechanics and deal with it. And then from then on, we had applications of quantum mechanics. Most notably, of course, the Manhattan Project. But we also had, MRI machines that are assisting us every day, at hospitals, particle accelerators that are very cool to talk about. Plenty of my colleagues are doing research on those. But then, after that, we have the idea of quantum computing pop up, right? There is this concept, maybe, can we create a computer using quantum particles as opposed to bits? Is there something there that we can leverage and use? And then in 1992, we had the first actual quantum algorithm developed. Okay, we can do something with this. This is not just a thought exercise. And then 1994, that's really when it hit the public consciousness with Shor's algorithm, and a lot of interest came about because Shor showed that a quantum computer, should we develop it, can break RSA encryption quite easily. And people went, ooh, okay, this is something we might need to pay attention to. This has applications, and if somebody develops it and we don't, that'd be problematic. And then 1998, we have the first demonstrated actual quantum computer being built. Right? It's not science fiction anymore, right? It's not Star Trek. We have it. It's here, and we're using it. That was really cool. In fact, a lot of the people who have these startups in quantum computing started off. They were the first people to develop these computers, and they just started businesses because there was a lot of interest in this, right? There's very cool technology. And then certainly 2016 is definitely when I became interested in this topic because IBM came out with their first cloud-based quantum computer. You can now go online and use a very small 5-qubit computer on the cloud. Holy crud, right? It's no longer abstract. I can go online and use a quantum computer. It's not something in a research lab. It's not something in some government facility miles away. I could go and use this technology. It made it tangible, applicable, and it did the same for a lot of people. And then Google claimed quantum supremacy in 2019, and that is a quantum computer was able to do something more efficiently than a classical computer, albeit they did it for something that wasn't the most applicable, but they're able to say we were able to do something that a classical computer, was it that they couldn't do it? A classical computer would take too long to realistically do this calculation?
What they did in 3 hours on a quantum computer should have taken a classical computer
to the end of
years,
death of the universe kind of thing. Yeah.
Something like 10,000 years, 100,000 years, something like that.
So actually showing that quantum computers, mathematically we've been able to prove before that they can do things faster or more efficiently than a classical computer, but it hadn't been demonstrated until then. So very, very interesting stuff. Leave it to you to do the math refresher.
Sure. So there are a lot of math out there, but luckily we only need linear algebra. So some of you may have an experience with it. We only care about a small subset of it, right? But for those of you who are less familiar with this concept, let's explain what are the basic building blocks that we have. So the things we care about are scalars. These are just numbers, right? Any number, like the examples we have here, you can think of them as points in space, right? A 0.5, something like that. You have vectors. They are one-dimensional. You can think about them as arrows. They are pointing toward a direction. They have a magnitude and a direction. And the next evolution, the more generalized form, is a matrix. Matrix is a 2x2 grid. You have all those numbers here. They can be a simple something. They can be more complex. But it's just a way to arrange numbers and use them more efficiently. Okay, so what we will care about are numbers, vectors, and matrices. You can do a lot of stuff with them, right? These are a subset of all the operations you can do on scalars, vectors, and matrices. We don't care about all of this. We care about two stuff. We will talk about how you multiply vectors. And here, there is one thing you need to pay attention to. If you take a lying down vector with an upside down, like standing vector, and you multiply them, we call it inner product, and the result is just a number. If you reverse the order, you will get a matrix, and it's called outer product. This is it. But again, we won't need to do all these multiplications. We don't need to calculate them. I just want you to know about what's going on behind the scenes, okay? The second thing is, again, a generalization of it. You can multiply matrices. You can follow this example. You can see you multiply this one with this one. You add this one with this one. You get the result. Why it works this way? Because this is how it works. We don't care for now why. Okay? So why we need all this kind of stuff, right? We need them because, abstractly thinking, they live in a vector space. Okay? So all those vectors which have shared properties, they live inside a space, abstract space. So for example, all the xy points you can think about, all the polynomials, all the 3x3 matrices, they have their own space. They all live there as one big happy family. This vector space thing, we have a basis. And it's kind of, you can think about it, it's like the directions you can go in this space, right? To make it less abstract, if we think about an xy point, something that we are very familiar with, right? We can take the point 3, 2. It means that you can take 3 steps on the x direction, and then you take 2 steps on the y direction, so you get here. So x and y, these are the bases for this vector space. Maybe an example that is less intuitive in the beginning, polynomials are also a vector space. So you can think about a direction for x squared, x and 1s. So you can write this polynomial as a point in this space. Okay? The entire idea of this slide is just for you to understand that we will talk about a vector space. It's an abstract thing that some other abstract things live inside. Okay? It's a way to collect stuff with similar properties. This is it. We're done with the map.
Yeah. So all that's to say is that quantum mechanics at its simplest is linear algebra, right? It doesn't get more complicated than that. Everything else we're going to describe can always be traced back to exactly what we showed you, vectors. You know, a lot of times you might hear about quantum and you might, what is going on here? All of it can be done in this kind of vector math and always brought down to that kind of level. And so when we're talking about, you know, quantum mechanics in general, there's a couple of conventions people use, right? When we talk about states, those are vectors. When we talk about operators, those are your matrices. And when we talked about Hilbert space, that's just the vector space that these particles are existing in. And when you have what's called that inner product, right? When you have the lying down and the standing up vector, that's going to calculate your distance for you. So all these calculations have inherently in them a sense of distance. Like we said, right, quantum mechanics isn't so intuitive. Actually, right, there's a lot of intriguing and non-intuitive concepts when it comes to quantum mechanics, right? There's things like superposition, that a particle can be in multiple places at the same time, right? Entanglement, that measuring one particle also means you're measuring another particle, and doing something to one will affect the other one even if they're spatially separated, right? There's things like, you know, measurement will collapse its quantum mechanical behavior and cause it to behave classically. And tunneling is a very fun one that people like to wax philosophical about, right? If you have some kind of a barrier and you have your particles, you know, probability distribution of where it can exist in space, if your barrier is sufficiently small enough, there is a probability that it will be on the other side of that wall, right? Going through the wall, the probability doesn't drop to 0. It drops, but if it's sufficiently small enough, there is a probability that it'll tunnel and be on the other side of it. So that's some really cool and interesting stuff, but again, not intuitive. And actually, this is a dialogue happening quite a few of the conferences I go to, is how do we make this more intuitive for everybody, for the general populace? And the concept right now is to start teaching quantum mechanics in K through 12 education, right? In the same way that we teach, chemistry or other concepts, math, right? You don't start off and talk about vector spaces, for sure, right? Right? When you're teaching chemistry to elementary students, you say, water can turn to a gas when it gets hot enough, and when it gets cold, it turns to ice. You stop, right? Full stop. That's your chemistry lesson. Middle school, you start learning about, what are atoms, things like this. In high school, you get to have more complex discussions about chemical bonds and things like that. So in the same way, there's a dialogue going on how do we introduce quantum mechanics at these different levels so it becomes intuitive, right? Things can be in multiple places at the same time, or, electrons behave like a wave and a particle, full stop, right? You don't have to teach any of the math. And one of the most fun examples of quantum mechanics is kind of this Schrodinger's cat equation, right? There's tons of stickers you can get on this and fun memes. But the thought experiment, and certainly nobody did this, so don't worry, but it was a thought experiment, right? There's a box that contains a cat and a radioactive ion, a radioactive atom, right? It has a half-life, so it means it's gonna decay, and it had a half-life of an hour. So there's a 50% chance that in an hour, this radioactive atom is gonna decay and kill the cat. So there's a 50% chance at that 1 hour mark. So without looking into the box, at that 1 hour mark, is the cat alive or dead? The radioactive decay behaves quantum mechanically, right? It's probabilistic. And so the thought experiment is, there's a probabilistic chance that that cat, this macroscopic thing, is alive or dead. And this spawned quite a few conversations, and quite lively ones too, right? Can you have macroscopic quantum mechanical behavior? And that's something researchers are delving into in a big way. We've had some small successes there, so quite interesting. You can see some, macroscopic, micrometer measurements, but still way bigger than quantum. And see some of this same quantum mechanical behavior happening, in front of your eyes. It's pretty cool stuff.
But we will answer this question later on. So don't worry.
Fear not. Let's see. All right, direct notation. Were you doing this one?
I got it.
Yeah, I'll let you take the linear algebra stuff.
Right. If you have one particle, it's really easy to write all those matrices and vectors and do the multiplication. But if you start to deal with a more complex system, like a bigger atom, right, or a molecule, then the matrices will show you later on, they just inflate and become like huge volumes and numbers. So Dirac was a physicist, and he came with a notation that it's a short way to write down everything and simplify all those multiplications we discussed, all those vectors and matrices and operators and states. So he called it bracket because it's in a bracket. And you care about those two parts, right? The cat, the other one, this is what we call the state. This is the vector or the state of the system that we want to describe. And it's opposite. So this is like the up-down vector, and the bra is the lying-down vector. Okay? We said that we have those states and we have those operators, and we'll see what they operate on or what they do. So we write them with this small hat, and it represents one big matrix. So it can be like million by million, but you just write O. Simple. We talked about bases, right? We need a basis for the vector space. The easiest way we think about it is you can either be 0 or 1, right? Same thing we have with normal computers, binary system. 0 and 1, these are the states. And then come the funny part. So we mentioned superposition. It's the ability to be at several states at the same time. So you say, what is my state? My state is something at 0 and something at 1. I'm at the same time, part of me is at 0 state and part of me is at 1 state. Now these alpha and beta, they have some constraints, they need to be normalized, so because again, everything boils down to probability, right? So eventually everything you have needs to sum up to 1. And then if we use this notation, it's really easy to expand it. So if we have now 2 particles, they can be both at the state 0, 0 and the other one at 1, 1 and 0, or 1 and 1. And if you're familiar with the binary system, you start to see the similarities and why people choose to use this notation, because this is how you count in binary, right? This is 0, 1, 2, 3, on and on and on. So we take advantage of it to make it simpler for us humans to think about this problem, so we use 0 and 1. And we mentioned those operators. So when I want to do something to my state, for example, I want you, Eric, I want you to move to the right. I need to operate on you, so I use move right operator. Like, funny example, but you take the operator and you operate on the state, and it will change, right? Something will happen to it. This is an example for a computation, right? So you do something to your information, right? We'll see later on how it applies, but this is how we write it down. And this is how you calculate the probabilities, but we don't care about this much for now. So what you need to remember from this slide, we use this notation to represent the state of the system, what we have in our computer, in our experiment, in our cat in the box, or whatever.
So I have one point here, just Greg, when you have the alpha and beta in front of those 0 and 1s, we call that the amplitude. When you square that, that's the probability of being at that state, right? So when you do the 0 and the wave, what you get is alpha squared and the probability of finding that particular state. So that's why you have to normalize it to 1, because all probabilities should add up to 1 at the end of the day, if you're doing things right.
This I won't spend so much time on it, but the thing is that a basis is not one way to think about it. You can switch bases, and sometimes it's easier if you just change your perspective on the problem, right? So it's a change of perspective. The result will stay the same. So for example, if we have this grid of points, I can tell you, Eric, I want you to get from point A to point B, and I can specify the direction going right, left, up, and down. But I can also tell you, do this weird move here. I can still get to any point from any point that I want. I'll just need to move differently. I change the perspective, but it's the same result. So we have the 0 and 1, and you'll see later on that we will use, when we'll show you how to see it visually, you will see that we also sometimes use plus and minus. Why plus and minus? It has 0 reason behind it. It's just an easy way for people to think about it. We have 0 and 1, plus and minus, up and down, things that makes it less abstract for us. It helps us think about the problem. Okay, that's the entire idea, and you can move from, you can translate this solution to this solution, you can switch between bases. And now we got to Schrödinger's equation. Technically, this is Schrödinger's equation. This is the Dirac's notation way of writing it down, so it's very compact, very simple. And sure.
When you say, I mean, it's intuitive to know like what right, left, up, and down is, but when you ask it to go like positive or negative, what does it do then? Like,
we'll get it. You'll see it.
Yeah.
It's just different direction.
Yep, right.
it's still directional.
It's still
Yeah.
direction.
I
Like
think there are 4 directions or more.
you can have more than 3D space.
Oh wait.
Yeah.
You can have more than 3D space. This is actually part of the things that makes it more advantageous than classical computers. See that you need few resources, and you can still hold a lot of information that on a classical computer will need like a full hard drive. You can use just few qubits to hold the same amount of information because you have all these directions you can go to. So we'll see the Bloch sphere, and then it will make more sense. The idea of this slide is just to show that behind the scene, the problem we are trying to solve is eigenvalue problems. This is what we try to solve. So Schrödinger's equation is the same thing. The important thing is we see again this cat, the psi in a cat. This is the system. So in this video, you have this particle moving inside the box. So what is the particle doing? This is the psi. H is the Hamiltonian operator. It calculates the energy. So if I operate with the Hamiltonian, I just get the energy. So if the particle moves like this, it has one type of energy. If it moves like this, it has more energy and more and more and more energy. So we will not need to solve these type of things, but that's the mechanics that happens behind the scene, right? This is the big revelation that started quantum mechanics. Once we were able to write it down, find the Hamiltonian for the specific problem we try to solve, then we can just operate on it and figure out everything we want to know about the system, how it will behave, how it will evolve in time, what we should expect from it to be doing and what it cannot do. So all this kind of stuff comes from solving this problem for a specific system.
And the system can be, right, this is used quite a bit in chemistry, right? So the system can be elements, right? How does, hydrogen behave? How does it evolve? And that's why, this was so important. When you talk about it in the state, it's abstract, but it's like, this is how you figure out quantum mechanically how different molecules are going to behave in time, how you simulate this using quantum computers.
So now that we know that we can use superposition and we know that we have Dirac's notation, if we go back to our poor little cat, right, after an hour, the state of the cat is in a superposition of dead and alive. Right, this is why you get all those funny things. The cat is one dead and alive. So unless we touch it, unless we look inside, if we just let it be, the physical answer is that the cat is both dead and alive at the same time. It's in a superposition. Of course, there are a lot of philosophical discussions about it. What does it mean? What if I was the cat? What would I have felt? Does it mean that once we'll open the box, then the cat need to decide, or do we split into multiverses and actually we're not in a superposition, so part of us will move in a universe where the cat is dead and some of us will move into a universe where the cat is alive?
Is the cat an observer? Does that count? Yeah, all those.
Does the cat, what the cat thinks about itself, right? So it's also a coin because the cat is sentient, right? So we have no right answer for it, but this is how we express it. So for us, the state of the cat is being dead and alive at the same time.
And if any of my professors see this recording later, I'll just say this is not a normalized equation. 1 over the square root of 2 on that.
Yeah. Let's simplify.
Yeah.
I had a question.
Sure.
We go back to the previous slide. So just to break it down to a very basic level, from this it seems that quantum mechanics is an explanation of uncertainty at a point in time. Because that's what this kind of is. You're not certain whether the cat is alive or dead. And hence it's expressed as an equation that caters to both possibilities. Mm-hmm. So my question here is it an explanation or is it a solution to uncertainty? Because this is true at a point in time. But eventually, irrespective of whether we check or not, the cat inside will be alive or dead. After that hour is passed, if it decays, it's dead. If it's not, it's just that we don't know about it. So, we're explaining uncertainty, but are we also solving for that uncertainty? And I'm linking it up to when you said this can operate across multiple states, right? So is that to understand what state or states a particular element might be? Or is it just to explain that it can be in any of these states and that's about it?
Well, that's a great question, right? One of the things that's very applicable even for chemistry, right? You can measure it at a point in time, or you can do the time evolution of it. And there is an operator to evolve your state over time to see at different points in time what it's what's its behavior look like, how has that evolved, and then you can see that across time, right? So it's both. Solving that, but if you wanted a time slice, you can get that solution as well.
And if you're solving for it, what's the basic assumption you start? And I would want to link it up to that example you showed about city planning optimization. And if you don't start from a particular supposition of saying this is where I want the city center to be, or this is the kind of transit time I'm looking at. And again, I'm simplifying it a lot because I don't know anything about quantum mechanics. So how do you identify what's a good assumption to start with or a good starting point?
That's a tricky one because that's true for any problem you deal with across the board, mathematics, business, anything, right? Your equation's only as good as your input variables, right? If you have incorrect input variables, you're going to have an incorrect solution at the end of the day. Right, that's.
So that can be subjective then. And then, which brings me to a third question: how do you know you're right or wrong?
I mean, that's all physics deals with, right? How do you figure out if you're right or wrong? It's experiments. It's experimental validation. Eventually, if you run the same kind of calculations over and over, and you see that time and time again, it's proven true, proven true, proven true, proven true, you can lax your parameters and say, probably the next time I do it, this equation will hold true, even if I don't know what the final solution is. I believe in this system and the way it evolves and the way we've been doing this so that I can go ahead and do that next calculation.
Oh, thank you.
A couple of things to add. You asked, how do you know which states you can see, right? What is allowable, right? What is allowed? We don't go about like the steps of solving the equation, but part of it is that first you say, okay, so my system can be either in psi 1 or psi 2 or psi 3, so the allowed state is part of the steps you take toward the solution. Then you figure out for each one of these states this amplitude, or like what is the probability of it to happen. And it gives you the answer that you will eventually get is the probability that you will find yourself in a given situation. Again, the uncertainty is always there. There is, like on top of it, you have a Heisenberg uncertainty. So no matter how precise you can measure yourself, you can know only certain stuff about your situation, about your state, but you cannot know everything. And another like philosophical kind of thing, because you said something which is very deep, but you probably didn't realize it, but not everybody agree on the interpretation of quantum mechanics. More than that, many people think that it's incomplete, or we have a lot of reason to think that quantum mechanics is probably an approximation of a much bigger truth or something that is happening there, because it works for a lot of stuff that we didn't know and weren't able to explain before, and now we can. But there are some small stuff which are still just doesn't fit there. So we know that there are missing pieces into this big picture. It's not complete.
Actually, one that I want to add too that's going to be important for later discussions is, since you brought up kind of this uncertainty in input variables, this is an issue for quantum computers themselves, right? There's something called coherence time, right? Your quantum particle that you're doing measurements off of will become more error prone over time. So you're doing all of your measurements off of it, assuming that your initial state is in this, 0 or 1 state. Like you assume it's in this clean, well-defined state, but over time it can vary. And the longer you take, the more it has a chance to vary. And so there is errors in quantum computers the longer your computation takes. And so there's a lot of work going into how do we increase that coherence time, how long that quantum particle will stay clean probabilistically. And then there's certain algorithms too on how do you mid-calculation clean up that error so that you can be certain about your calculation. So again, right, your calculation is only as good as your input variable is what you think it is.
So I'm trying to link it up to this concept of a random AND that I read somewhere, which says that if you leave a random AND, it's again a computer simulated thing, that says if you just leave the computer to decide where it will go, over a period of time, it will develop a pattern.
The random walk.
Yeah, the random walk kind of thing, so it goes all over and then you'll see one pattern emerge. Is that kind of linked to it? The initial input is clean because it has no pattern, and hence it can behave anyway. But when it starts developing a pattern, it's then kind of constrained by the fact that it's been in the system for so long that it's developed a pattern. So just try to figure it out. When do you decide whether the input variable is no longer clean?
Yeah, I've never linked the two concepts together, but certainly that's a way to think about it, right? Over time, it's going to wander away from what you think it should be, that initial state. And so at some point in your calculation, you need to have some kind of cleaning calculation or a way to observe, oh, this person's farther away than they should be, let's snap it back, or things like that. Absolutely.
Well, Eric mentioned entanglement, right? So let's try to understand what's unique about it, because this is one feature that we will use heavily when we run the algorithm. So let's make sure that we get it clearly. Entanglement is like correlation that we learn, normal correlation, but kind of stronger than that. It means that if you know something about a part of your system, automatically you know something about the other part of the system, right? And the key word here is instantly, right? So like a classic example will be if you have this pair of shoes, I'll take each shoe, put it in a box, close them, shuffle them around. You don't know which pair is in which box. One I give to you, the other one I open. If I see that it's the right shoe, instantly I know you have the left one. So it's a lame example, but this is what entanglement is all about, right? It happens again with quantum particles. So if you have electrons, their spin or something like that, they have properties which are linked together with this entanglement. And if you do something on one of the pairs, you automatically know about the other one. So this sharing of information is something that we can take advantage of. And not everybody liked it, so Einstein, Podolsky, and Rosen, they called it spooky action at the distance, because technically we say nothing about the distance between those two things, right? I can have this box here, and the other one I can shoot to the other side of the universe, open it there, and still I know instantly which box you have, which shoe you have. So does information travel faster than light and all this kind of stuff? So they didn't like it, and then came a guy called John Bell, and he showed that no, there are no hidden variables and other stuff. This is how it works. Regardless of distance, regardless of speed of light, it just happens. This is it. So either you accept it or you deny realism and locality and all these kind of like philosophical notions we believe are true. So you just need to accept the fact that it happens. And now, Fatima, for your question about the zeros and one and the directions and the space, this nice guy, David Hilbert, he was a mathematician, and he discovered those Hilbert spaces, and we can take advantage of it because they are huge, like huge. There is a lot of space there. And a nice way to think about it and visualize it is using this Bloch sphere. Okay, so imagine you have a ball, and you can be on any point on the surface of this sphere, right? A classical computer, if you have a bit of information, a transistor, it can either be 0 or 1. So a classical computer can be either here or here. This is it, you have 2 points. We can be all over the sphere. So even if you don't mathematically understand what it means, you see that there is a lot more space to be in, right? You have a lot more information or more complex information you can hold if you're allowed to move away from just this point and that point, right? And if you think about like this superposition we said, this is exactly being slightly here or slightly there. And if you can assign a meaning to this being either here or there, then you're making more complex calculations with just 1 qubit, right? So because you have more space, 1 qubit holds more information than 1 bit. And this is like a visualized way to show it. So how many combinations you can express. So with classical bits, if you have n bits, you can have 2 n states. So for example, if I have 1 bit, I can either be 0 or 1. If I have 2 bits, I can be 0, 0, 0, 1, 1, 0, and 1, 1, right? I can count up to 4. If you have qubits, they actually scale like 2 to the power of 1. So a classical computer will scale the memory or the calculations that you can do, they will go like this, where a quantum computer will go like this. And because this gap is getting bigger and bigger the more we add qubits, this is why we want to have a lot of qubits on a quantum computer, because then we can have a lot more space to do the calculation. We can have a lot more information at the same time.
This also shows why it's very difficult for a classical computer to simulate quantum systems, because the larger your quantum system becomes, it scales outrageously, and a classical computer just has a hard time simulating anything very large quantum mechanically.
And now going back to our cat, which we talked about. When we talked about the cat, we kind of stopped at this point, right? Where the box is still sealed. We don't know what happened to the cat inside. We just said that it's dead and alive. But we do a calculation, right? Even with a normal computer, we do a calculation. We want to see the answer eventually, right? We want to have some kind of measurement and see 1 + 1 = what, right? So you need to have a measurement. So we open the box and we look inside, and here people disagree. This is going back to the multiverse or wave function collapsing and all these kind of explanations we try to give for something that we don't really fully understand. So we said that the moment that we open the box and we observe, this superposition collapses and the cat needs to choose to become either dead or alive. So it's no longer in a superposition because we looked at it, we observed. Now the cat is either dead or alive. Again, we have no final way or one way that everybody agrees on top of it. There are a lot of interpretations for quantum mechanics. This is one of the open questions that we have. We just know that we have a system, when we don't touch it, it's in superposition. The moment we look at it, like Eric mentioned, the 2 slits experiment, as soon as we look at it, it collapses, it chooses one state, and continues from there. All right, so a lot of stuff. Let's like a quick recap. So we talked about like what the phenomena that led to the evolution of quantum mechanics. We talked about the linear algebra, operators and state, they live in this Hilbert space. We showed you the Dirac notation, which makes it simpler to write down. And the main properties we will use is the superposition, being in 2 states or more at the same time, and entanglement, this spooky sharing of information. And now we'll show you how we can exploit all this stuff to build a quantum computer.
All right. All right, so here's the fun bit, right? To talk about quantum computers, you have to first define what is a computer, right? Right, computers are systems that use bits, right, 0 or 1 to do calculations. And it's simplest, right? It uses logical operations and from kind of Boolean logic, right, and or not statements, you can do algebra, right, simple math, subtraction. You can take that and do, multiplication, division, and once you get to multiplication and division, you can do almost anything. So computation is the act of manipulating these states. Typically, we use like the silicon transistors to perform these Boolean logic operations. But again, right, computer is a system that uses binary bits as its fundamental calculation, right? So even reading a CD, it's weird, I had to tell my daughters what a CD was. Odd one for me. But the groove that the laser etches into a CD is the 1, and the flat is the 0. Or I forget it's the other way around. But it can read the information like that because it's a binary system. So it can use any kind of binary system. Just happens to be that transistors are very good at being compact and excellent things for computers. And a Turing machine was a machine at some point, but it's kind of the abstract idea of what is mathematically possible for what a computer can do. It's often used for experiments or thought experiments to figure out what are the limitations of classical computing. And what a Turing machine is a system, right? Conceptually, it's a system that has a rule set. Given a rule set and input variables, it will give you a solution, some kind of solution, right? In the day, it was, the solution came out on a ticker tape, but that is essentially the limitations of computing. So a Turing machine, hypothetically or theoretically, can do anything a classical computer can do, and it kind of sets the bounds for that. So what are quantum computers, right? Quantum computers is fundamentally a new way of computing. It's not simply kind of building off of classical computing. It's a whole different way of doing calculations, right? And you can think about some of the quantum mechanical principles we've talked about in classical terms, right? We talk about superposition. You can think about that as parallelization, right? You have all these, if you have 4 bits, you can have so many, a certain size bit string. A classical computer can hold 1 bit string at a time in those bits. A quantum computer can hold every possible variation of that bit string at the same time. So you can think about that like parallelization. We'll talk about that in a second. It's not exactly true. Entanglement, right? You can do more complex calculations at a single time, right? Like I said, you have all these multiple states can be held. Hilbert space is terribly efficient space to do calculations on because it's inherently mathematics in this vector space. It has a sense of distance built into it when you're doing calculations. And data transfer, right? For a computer, you have electrons flowing through wires. For quantum computers, you mostly have photons being transferred through optical wires, right? So you have a lot of these systems. We'll talk about the different ways to create quantum computers. A lot of ways that this data is transferred is a laser goes and probes your quantum system, gathers that information, and sends it through optical fibers.
I think the idea here was like we said that it's not an improved way of classical computer. It's entirely different way to achieve the same thing. And then the example is if you have your internet connection runs on DSL, right? You have copper wires and you have electrons flowing. So use one type of physics to move data from one end to another. But you can also use optic fibers, and then you're using photons, and it's like different physics. You're doing something differently, but the idea is, again, just to move data, right? So you can do those calculations, but it's not improved, it's like entirely different physics. It's just different.
Yeah, certainly, and we can expect certain performance improvements using a quantum computer over a classical computer for certain types of problems, right? And that's the bit you have to take away when you talk about quantum computers. It's not going to do everything. It's not going to solve all the problems in the world, right? I was saying with you on a call, last week, I don't anticipate, quantum computers being able to do Zoom calls anytime soon, right? They're very good for certain classes of problems. They can't do everything. But they are going to be, and the thought right now is they're going to be part of the supercomputing infrastructure, right? Part of this, high performance computing ecosystem. In the same way that you have, yep.
Yeah, for quantum computers,
Yeah.
to solve classical problems or problems that we usually solve on classical computers, do we need new formulas for using that superposition state and all those new properties?
Absolutely. Yeah, there's different kinds of algorithms to do basic things. Even in the workshop, we'll show you how to do like addition, subtraction using quantum computers. It's a fundamentally kind of different way to deal with your things because it's probabilistic, right? It's not just 0, 1.
Right, so we have to change completely the way we do those computations.
Yeah.
Okay.
Absolutely. Yeah.
We'll get to the point, right, where we'll start to talk about algorithms and when
Mhm.
you will actually do it, right? It's entirely different way. Like you use Python, right? It's a language, the syntax but when you want it to do something, you don't tell it like just add those bits and you get it. You need to tell it like rotate and move and switch and move. It behaves differently. So I think part of the things we'll discuss later on in this class is that you need to change the way you think about algorithms and how you do stuff. And this is part of the challenge.
Okay.
Yeah, and part of what we're going to show in this class too is that this is the kind of the tricky part in programming quantum computers, right? Changing your mindset, creating those algorithms that are the mimic to classical computing. But modern technologies and new platforms are simplifying that out, so you don't have to even worry about the different way of thinking about it. You can go ahead and tell the system, do addition for me in the same way you would do that in Python.
Right, so you have to develop a new language.
Pretty much, yeah. So there's we'll talk about that more in depth in tomorrow's lecture. Certainly, it's a topic I love because it's something my company does. So, but one thing I just wanted to end this slide on was saying that the future for quantum computing at the end of the day is going to look very similar to programming anything else you've dealt with if you're a software engineer. When you're dealing with computers or working on supercomputers, right? You have your CPUs, you have TPUs, tensor processing units, you have GPUs, and you send the bit of your problem that's easiest to be solved on the GPU, send that to the GPU. You send certain problems to the CPU because that's more efficient to do that calculation on that. Eventually, we're going to have QPUs. We're going to have quantum processing units, and you're going to send certain classes of problems to the quantum processing unit when that's the most efficient way to solve that problem. Same way we work with any other technology, in that kind of infrastructure. So there's a lot of work right now to hook up quantum computers to supercomputers and start that interaction. All right, so how do classical and quantum computers differ, right? We talked about classical computers. Fundamentally, it uses bits, right? That's fundamental computation. 0 and 1, and everything goes off of that. There's, of course, physical limitations on that. Transistors are getting to a point where they're getting so small that they're starting to have quantum mechanical errors pop up. Quantum tunneling is an issue now. Because our transistors are so small, the electron can tunnel through your transistor, and so that's problematic, right? Your logical gates no longer work if it can tunnel through. So we're hitting some kind of a fundamental limit that we can get to how small we can take classical computing. So people are trying to think of new kind of architectures. How can we redo this? Can we have stacked transistor layers, things like this? There's tons of issues with that, like heat dissipation. But it's mostly computation using this. What a quantum computer does, instead of binary 0 and 1, it uses quantum particles to do this. Quantum particles also have two states, right? It can have a 0 and 1 as we showed before, but it can be in this superposition. It can be somewhere between 0 and 1, and that's kind of the cool thing we can use and manipulate. And some brilliant people have come up with really cool algorithms on how do I use this extra, ability to do calculations. How do I leverage these quantum mechanical particles to do cool things? There's a lot of ways to create a quantum computer, right? Because there's a lot of ways to create a quantum bit. You have electrons, right? You can have an upspin, you can have a downspin. They can also be in superpositions. You have light is a quantum mechanical particle, right? It can be the polarization of light. You have p polarized, s polarized, but it can also be in between these states. So certainly there's quantum computing companies trying to make optical quantum computers. There's simulated atoms, right? The superconducting qubits are always fun. And a number of companies that use artificial atoms, right? That they're coming up with, and there's also trapped ions where they're trapping these particles and then doing calculations on them. So there's a lot of different ways to create your quantum mechanical state. A lot of them right now require these ultra low temperatures so that they behave quantum mechanically, and that's one of the limitations on some of these technologies, that you do have to reach these ultra low temperatures so that A, your technology behaves quantum mechanically, and B, so that other things don't interact with your quantum mechanical particles and cause it to behave non-quantum mechanically. So going to what we were talking about before, how do you program these things, right? In classical computer, we have gates, right? You operate on a single bit, and you say, if my input is A, the output's not A, right? So that's a NOT gate, things like this. So you have these Boolean logic going on with it. And so with enough of these, right, you can do addition, subtraction, and quantum mechanics, instead of having Boolean gates where it's if, not, or, you have spins. Instead of just 0, 1, you say, I'm going to rotate it in the x-axis or in the y-axis, and those are the gates that you run your quantum particles through. And this is the difference in how you have to create these algorithms. Instead of thinking Boolean logic-wise, you have to think rotationally and probabilistically, and how those rotations change those probabilities, and then create cool algorithms off of that.
These are the rotations.
Yes. So these are the rotations, right? You can rotate the x-axis, the y-axis. H here, we're talking about, that's the last bit on this chart, called a Hadamard gate. Rotates, it changes the basis, right? So most of the time when we're using quantum computers, you measure in a basis, and everyone kind of disagrees. We're doing this in the z basis, so that when I read your program, I get the same solution. But Hadamard gate changes the z-axis to the x-axis, and what that does for your solution at the end of the day is it mixes the probabilities. If you had a particle at the 0 state in the z-axis, well, now it's going to be in an equal probability in the x-axis of being, plus minus. So it just perfectly mixed that probability up. So there's a lot of cool things, right? There's analogs to the NOT gate. There's analogs to kind of this Boolean logic that you can perform with quantum gates. But again, you have to think about it in this rotational way.
So
Yeah, go for it.
we will use it later on when we will start the hands-on parts. So we put those like animations here so you can actually understand what we mean by all those rotations and what the operators are doing. Okay, so these are the block spheres like we saw before. We see 0 at the top, 1 at the bottom. So this is your z-axis for the sphere. This is the x-axis. We called it plus and minus. You also have the y. We call it plus I and minus I. Ignore the namings. But the idea is you see the arrow pointing at a certain point. So wherever the arrow is pointing, this is the state of the system. This is the psi in the cat notation. This is it. And now, at the top, for example, you have the x operator, right? You can write it again as we saw it. Everything eventually is matrices and vectors that we multiply. So if you want to go back to linear algebra, this is how you write an x gate or x operator. But what it's actually doing, when you operate on your system, it is kind of like taking your arrow and rotating it around the x-axis to point down. So you turn in 0 into a 1. And if you do it again, you turn 1 into a 0. This is why we think of it like a classical NOT gate, right? You turn 0 to 1, 1 to 0. Same thing here. But again, we said that the Hilbert space is big, so you can move to any direction that you want. So you don't have to rotate just about the x-axis. This one, if you carefully look at it, it's kind of the arrow is kind of coming toward you and goes back and back to the top. The Hadamard gate is a change of bases, right? We mentioned that we can use different bases, it just changes the perspective. So now when I start, my arrow is pointing towards 0, so I'm on the 0, 1 basis. But if I apply it once, it's kind of doing a funny rotation, you get to be at plus, right? And then I can actually play on the x-axis, right? I can do stuff around here, and then I can apply it again, and I can move back up. So, and here this is just a mix. So we do one thing, and then we do another thing. So we rotate this way, and then we apply a different thing. So there are a lot of ways you can get back to the starting point, and this is a calculation, right? This changing where the arrow points, this is the calculation that the quantum computer is doing. And if we can assign a meaning to it, what does it mean for the arrow to point here or there? Then we have an answer for the question, right? So this is how you build the question. This is how you build the quantum algorithm. You think, okay, I need to rotate it here and then, and if I do like a backflip, then I got my answer. So this is how you need to think about the problem. This is part of the challenge.
Yeah, and certainly some brilliant people turned this into usable, tangible algorithms that you can get, outputs from. In the same way, brilliant people turn 0 and 1 into, iPhones. It takes a lot of knowledge and expertise, but you can do a lot of cool things with, interesting starting points.
But if we kind of expand the problem, and now we don't have just a single qubit, we have two of them, we need to account for more combinations of them, right? So it becomes problematic to visualize it because it's kind of like a 4-dimensional space now, so we cannot visualize it. But this actually is supposed to be an example for why we like the Dirac notation, because look at how compact it is to write 0, 1 and switch it to 1, 0 instead of writing this one big matrix. And this is just for 2 particles. Mm-hmm. If we have 3, we come 2 to the power of 3, so it becomes 8 by 8 matrix. And it inflates really, really fast because you cannot really do a meaningful computation with 2, 3, or 4 qubits. You need 100, 1,000. So you will have a matrix of the size 2 to the power of 1,000. So this is why we need this notation.
Essentially, right, there's also the concept, like you said, of multi-qubit gates, doing things on multiple gates simultaneously. So we have gates that will swap your bases, right? Sorry, swap your
the
direction, yeah, from 0, 1, 1, 0, right? Just flip them around. And then we also have NOT gates, right? Depending on what the state of one qubit is, it will flip or not flip the target qubit.
It's like an if statement, right?
Mm-hmm.
If one qubit is to one situation, then do something to the other one, or don't.
Yeah, so you'll see a lot of quantum computing programs talk about things in single qubit and multi-qubit gates. Multi-qubit gates are always a little bit harder to deal with, so you want to kind of limit those as much as possible. But most everything can be broken down into either C-NOT gates or some kind of single qubit rotation. You can always kind of break down your calculations into these fundamental building blocks. Let's see. Oh, complexity classes. This one's fun. So right, we talked about the kind of big O notation on what that means. It's kind of this order of magnitude, how scalable something is, what that looks like. Now, this is one of the reasons why we're looking at quantum computers in the first place. We know theoretically that there is a class of problems that quantum computers can solve more efficiently than classical computers. There's all these kind of letters here, but what this is showing you is that there is a class of problem in kind of this thing we call p-space. P-space is a class of problems that classical computers can solve in a polynomial amount of time. P problems are problems that are easy to solve and easy to verify. NP problems are problems that are difficult to solve but easy to verify, like unscrambling a jumbled bunch of words, right? If you have a jumbled bunch of letters, unscrambling that can take a hot minute. But if you see the solution, you can immediately say, all right, that is a valid solution immediately, real quick to just check that. Figuring out what that word is from the scramble takes longer. Or in the example shown here, right, this is another example of the traveling salesman problem. What's the shortest path between all these points? It takes a long time to calculate how do I connect all these dots if you just have the dots, but if you have the solution, it's easy to verify, yep, that is the shortest path. Awesome, cool. Now there's go for it.
If you think about like Amazon will be highly interested in this kind of problem,
Oh, yeah.
right? Because they calculated a path they need to follow, but then someone came and have a new order and they need to put it also inside. So now they need to go and calculate all the possible options all over again, or they can solve it with a quantum computer and get a better solution and much faster. So the thing is, the classical algorithms we have, the only way for them to go about it is brute force. They map all the possible combinations and they calculate one by one how long will it take. And here we'll show you that you just set it up, get the answer.
Yeah.
So logistics and all these kind of things can highly benefit from this type of technology.
So when you set it up and you go and it comes up with the most optimized route, can you then put additional input? Like for example, when you go on a route, well, you have to go around the curve as opposed to if there are limitations that are only observed by the people who are delivering the packages, can that then be like put on top of it on like very specific parts of the path?
Yeah, so you want to kind of add constraints to the problem, right? You can do it.
All along.
Well, that is essentially a new problem to go ahead and solve, but quantum computers, because they can do it much more quickly than a classical computer, you have the possibility for dynamic rerouting, right? You hear every once in a while, right, the Suez Canal or kind of one of these major, throughways for cargo ships gets blocked. Happens sometimes, and whenever that happens, every Amazon shipment, every company is delayed by a month, a couple of weeks at least, right? Well, when that kind of happens, figuring out an optimal route, how do I go about it? Can I go and ship my packages a different way, faster? Or should I just wait for this to clear up? These kinds of calculations take a lot of processing time, so it's not very quick to make that decision. Quantum computers are going to enable more dynamic rerouting of things should some kind of hiccup occur, or if you're in the UPS truck eventually, right, I can envision a future where, oh, there's a roadblock here. Didn't see that before. Maybe a traffic accident happened, road construction. Let's reroute this. So it definitely opens up the path for dynamic optimization, where, as before, you needed the supercomputer to just kind of brute force this, as many simulations as you could until you said, that looks like it's the minimum. I'll stop.
Or you can take less than optimal solution.
Yeah.
Right? You can say, okay, it's not the best one, but I'm willing to spend 4 hours of computation and I'll just take the best result that I have.
Mm-hmm. Actually, that's a great one. A class of problem that fits into this, right? Because quantum computers can solve certain problems that are in this NP space faster than a classical computer, right? The problems that are easy to verify but difficult for classical computers to solve, certain of those problems classical computers have an easy time solving, like prime number factorization. That's why Shor's algorithm is a thing and why we're worried about security in the first place. But also there's things like the Monte Carlo simulation, right? Monte Carlo is a financial calculation, happens in way too many calculations if you're taking any business classes. But there's a quantum analog to the Monte Carlo simulation, and the confidence interval doing it on the quantum mechanical system scales down much more rapidly than classical Monte Carlo. You can get to more optimal solutions in a shorter amount of time steps. So, that one's highly applicable and why kind of finance is really big in quantum computing in the first place, and we'll talk about that more tomorrow. But that's kind of why you're seeing so much interest in this, is that there's certain problems that have a lot of business value that quantum computers have a promise to solve faster, more efficiently, more dynamically than their classical counterparts. We were talking about some of the things we just did. So yeah, there's kind of this QM space, right, that quantum computers can solve more efficiently than a classical computer, and there's certain speed-ups in these calculations over their classical counterparts. So unlike, like machine learning, where it's a miracle and it works, and we're not really sure why it works more efficiently than other algorithms, quantum computing, we can mathematically verify. There are certain algorithms that a quantum computer will be able to solve more efficiently than a classical computer. And that promise is tremendous, right? And why you're seeing just so much development. Anything you wanted to add to the slide?
Like, if you want to think about like visually what are people after, you see the orange circle is like the P and the NP part, and we have the BQP, the yellow ellipse. All the things that are in these yellow ones, if they touch the green part, these are the stuff that now we know we can't solve. We can just verify a solution, but all of a sudden you can solve it. But there is also just the yellow part, which are problems before we couldn't even solve or verify at all. Now we can actually do new stuff, which we couldn't do before. So this is why people are actually after to solve those NP problems and gain new insight to the BQP part.
Mm-hmm. All right. Practical measurements. All right, so let's see.
Yeah.
I'm curious about encryption algorithm. What about, for example, privacy and all related with encryption in terms of security? Because until one extent, it's true the fact that there are currently some algorithms that are quantum. How is that possible if they can actually calculate all possible combinations?
Great question. Actually, the reason quantum computers are going to break encryption in the first place is pure serendipity, right? Happened because we picked RSA, right, prime number factorization, as our primary way of encrypting data. It just happens to be that prime number factorization is a very easy problem for quantum computers to solve. So now what we're doing, and kind of what NIST is doing, right, the National Institute for Standards, is identifying other encryption methods that are difficult for quantum computers and classical computers to solve. And so what you're going to see is kind of NIST saying at some point, everybody, let's move over to this new encryption basis. This is what we're going to do and standardize around that. There's a lot of work and discussions going around about which of these encryption methods are useful for this. Certainly there's a bunch of companies right now that are saying, if you're really worried about this, we'll help you transition to one of those immediately. Right, that's why we're seeing this in the first place. And certainly there are classes of problems that both classical computers and quantum computers will take a really long time to solve, and that's what we're looking for. And we'll move over to those. The whole dialogue on kind of the cracking encryption is a worry about, how long is your data going to be viable for, right? Quantum computers right now can't crack this encryption in an efficient amount of time. But we're seeing something called, right, take now, decrypt later. So they're gathering, right? Bad actors are taking in lots of encrypted data so that in 5 years, when the quantum computers are powerful enough and sufficient enough to decrypt them in a certain amount of time, they'll decrypt it at that point. So they're just gathering it now, and in 5 years, they'll go ahead and decrypt it. So as a company, right, you just need to look at how long is your data important for. right? If you're, in real estate, don't worry about it, right? It doesn't matter. Your data is not going to be important to anybody in 5 years. If you're a government contractor, if you're in banking, okay, some of that can be still important and useful in 5 years, and so you need to be looking at these standards and when they change. Yeah.
I think like the main point is that just a coincidence.
Yeah.
It's a coincidence that we chose RSA and a coincidence that shows algorithm can factor this number. Pure coincidence.
Exactly.
And I think like we hope that the new algorithms that they will choose for encryption, we hope that in the future we won't find a quantum algorithm that can break it again. But it can happen theoretically, right? Because we don't know all the algorithms now. Someone might discover something and break all the encryption again.
But there must be some things or some sort of computations that even a quantum computer has trouble computing, right? Or
Yeah, certainly, right there. There's the whole. If you go back, there's certainly bits of problem space that are difficult for all computers, classical or quantum, to solve. And so we're trying to look for that. Right now, there is a discussion on what the limitation of the quantum mechanical sphere is for this, and that's why we're saying we hope what we pick will be in the long.
If you look at the top, you see the pinkish one, QMA hard. We know it's supposed to exist. You can show mathematically that it exists. We just don't know what falls into this category yet.
okay.
But there's supposed to be problems which are hard even for a quantum computer to solve.
Okay, thank you.
So, right, for brevity, what this slide is showing you is that classical measurements measure things, right, using memory and registers, right? It measures things classically, right? There's algorithms, you run them once, and you get a solution. Quantum measurements, right, you handle them probabilistically. At some point, you have to measure them and get a solution out of it, so it becomes classical at the end of the day, your data. But you need to convert that to one of your vector bases, right? Which angle are you going to be measuring your data at? So everyone's kind of just agreeing we'll measure it at the z-axis, and so when you program your stuff, make sure that it makes sense for the z-axis at the end of the day. So we're starting to come up with these kinds of standards across computers and algorithms and how we do software. And you have to measure these things more than once. Where a classical computer, you run the algorithm once, you get your solution, done, because it's logic-based. For a quantum computer, because it's probabilistic, you have to run it a few times. What we'll show you right in the workshops is when you run these algorithms, you run them a minimum of like 1,000 times, and then you get a histogram of your solutions. The bars that are highest on that, exactly, the bars that are highest are your solutions. The rest is probabilistic noise. But in the same way, you can have a solution or see that there are multiple correct answers to that same problem. Just, which are the high bars in there. Let's see. Oh yeah, and we call, right, the multiple runs of this, we call this these shots. How many shots are you going through the quantum computer doing this algorithm multiple times? Yep, and then aggregating distributed. I have a histogram or a density matrix or however you want to go ahead and visualize this. I just tend to do histogram.
But this is like, that's the output, right?
Yeah.
So if you look at like the example to the left, you define a variable x to be classical, then you say print, 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 you get the exact same result because it's a classical algorithm, no probability into it. You can introduce probability and non-determinism in classical computer, but most of them are, you just get the answer. It might take a long time, but you will get the answer. This is the answer that you get, and now we need to make sense out of it, right? What does it mean that this is taller than the one in the back? So this is what we need to think about when we look at the answer that we get.
All right, yeah, parallelization, right? So this is one of those kind of misconceptions. I mean, I even certainly talk about entanglement as a form of parallelization, but it's a fundamentally different way of doing computing, right? It's natural and easy to think about quantum computers in classical computing terms, but fundamentally entanglement isn't parallelization. It's the ability to do these calculations in a probabilistic way, right? You're getting multiple solutions at the same time, but it's not doing that parallel thing. There is parallelization that we're thinking about and trying to figure out how do we hook up multiple quantum computers together to do actual parallelization, but that's a problem actively being solved. Time for a recap. All right, so quantum computers, a new way of doing computing. It's not an improved way of doing computing. It's a fundamentally new way of doing calculations. It's going to enable some speed up of classical computation, but also it's going to open up new classes of problems that we've never been able to solve before. So some people are interested in it because it can do slightly faster Monte Carlo, and some people are interested because it can actually simulate quantum mechanical behavior that we've never been able to do before. Right? It's going to open up new possibilities. And so, right, we borrow aspects of how do we talk about this from classical. We talk about, gates and bits, right? Instead of a bit, it's a qubit. Instead of Boolean logic gates, we have rotational gates. We use the same kind of language, and what you'll see later too is we use the same kind of architecture when we draw it, when we program it. There's a lot of analogs here. And a block sphere is a way to visualize some of these rotations, and you'll see that when you go into IBM's environment that is in the workshop. Yeah, certainly. And there are certain problems that show advantage or what people call quantum supremacy. That's a fun word. You'll see a lot of people throwing around, oh, we've reached quantum supremacy for this problem, right? We've done it better or faster or something that a classical computer couldn't do. So a lot of people who have quantum computers or are developing this and doing benchmarks want to hit supremacy in one way and then publish some PR article saying, we've done it, and have that fun. All right, building quantum computers. Here you go.
The fun part.
I had a question on the previous slide. How much cheaper or more expensive are these to build and run? Or set up a problem?
Well, it depends on how you're accessing that quantum computer. I think it's in a slide we'll talk about in a second, but I'll answer this one now. There's a couple of ways to access quantum computers, right? You can buy a quantum computer, right? There's companies like D-Wave that are selling them, tens of millions of dollars. You can buy it though and have it at your facility. That's actually a slightly different way to do quantum computing than what we're talking about. There is a different type of computation called quantum annealing. We're not talking about that this class, and what we're talking about is gate-based quantum computing, and kind of where the industry is moving forward with. Certainly there's lots of applications for the other type of quantum computing. You can get into that dialogue probably during lunch if you want, but you can buy your quantum computer. You can go ahead and work with a facility that has a quantum computer and buy time on it like you would a supercomputer. And then there's companies like IBM and Amazon Web Services that have cloud-based quantum computing that you can just hook up to, buy a couple of minutes on it, and it's pennies for minutes. So I don't know what the price of supercomputing calculation is right now, but certainly if we want, I can show you during lunch. Amazon has it quite nicely written out. Here is the cost per minute run on these systems.
If you go on AWS, it will cost you like $30 an hour, depending on which system you take, but about $30 an hour. To build them and develop them, millions and billions of dollars. It's like, think about like Intel, for example, now they're building 2 new fabs at Arizona. It will cost them $20 billion just for the building itself. Right, so
But that's not for quantum computing, the fab they're building.
no, but it's the same idea that you need to build those facilities, and then you have all the R&D that you need to invest until you have the first chips, and then you need to make them.
I used to work in cryostats and ultra low temperature physics, and so I know some of the infrastructure needed to create at least one of the more popular modalities of quantum computing is superconducting qubits, and they require ultra low temperatures. So you need to put these into these giant dewars, these giant vats of super cooled gas. Essentially, it becomes a liquid when you supercool it. But you need to have this infrastructure to be able to cool it down to those levels. Maintain all of your gases, keep it in the system. To get to ultra low temperatures, you also need to play with magnetism in an interesting way. So you have to have ultra high powered magnets. You have to have your system isolated from the environment in certain ways too. Certainly the way we had it in our lab was the whole Dewar rig was there was a kind of metal frame, and it would be held up in this metal frame so it wasn't touching the ground. But even the ground that the frame was on was physically separated from the rest of the building, and at its foundation was on a bed of sand to even remove it from any kind of vibration. Because when you're at ultra low temperatures, even small vibrations can affect your system. So there's a lot of infrastructure you need to create to reduce heat transfer, vibration, and
Space
that costs.
radiation.
Yeah, exactly. That costs a pretty penny.
Yeah.
Alright? Alright. Before we go and build something, right, we need to have a plan. Right? We need to define what we actually want the computer to be able to do, and then we need to think about some requirement. Then you kind of need to think through how you actually achieve it, right? So we had this guy, DiVincenzo, he came with the 5 must-have requirements. So the first one, you need to have well-characterized, similarly behave, and scalable qubits. Okay? What it actually means, you need to be able in your facility to build a lot of qubits, and you want them to behave about the same, right? If one is really fast and one is really slow, it's problematic to have and build like a big computer out of it. Second one,
This is Eric Garcelle. Is this the catering order?
His mic is still on.
I think it's
So this is the building. Oh. Hold on a second.
the second thing is you need to have kind of like a reset button, right? You want to be able to say, okay, this is where I start, now let's do the calculation, right? So you need to have kind of like a reset button. Eric mentioned the floating and the cooling and all this kind of stuff. You have noise that you add into the system. Like I said before, you're not really sure where you are. You're supposed to be here, but maybe you're there. So we call it coherence time, for how long you're certain about your state. And if you have too much noise, then you just lose track of whatever is going on in your system, and it's just garbage in, garbage out. You need to have this universal set, which means you need to be able to do all the operations you want, right? So if you build a computer that can add numbers but cannot multiply numbers, it's a problem, right? If you can have for loop but you can't have a while loop, you can go on, but it will be a problem eventually. So you need to be able to do all the stuff that you mathematically want to do. And of course, you need to be able to measure your system eventually. And you need to be able to measure a single qubit. So what is your state? I want to know about you. Don't touch the other ones, just you tell me what your state is. If you have all of these in your system, it's a good start. Now we can kind of try to think how we implement it. So Eric mentioned we call it modalities or architectures. And basically, it all comes down to this idea of, can I find something in nature where it has 2 levels, this 0 and 1, and I can for certainty say, if I'll measure you, you're at 0 or at 1, and I can move between them. So we'll see later on which company goes with which, but you have those superconducting qubits. It's usually made of aluminum, this type of like rings and all this kind of stuff. You connect them in a special way, and all of a sudden, it behaves like a qubit. This is IBM, Google, kind of what Microsoft is doing. Photonics, Eric mentioned the polarization of light, right? You can rotate light. This is how actually 3D movies work, right? You have one polarization to one eye, another polarization to a different eye, and you get it together. You have some companies going about it. China is heavily betting on this technology. Ultra cold atoms, think about you take an atom. One atom is exactly the same as all the other atoms, right? They are identical. So if you can hold them in a grid and then talk to a specific atom at a time, you have a quantum computer, right? You can do the same thing, not with atoms, with ions. You take a couple of electrons out, and then instead of using lasers to hold them in place, you can use electromagnetic radiation. You can have quantum dots. This is, Intel is trying to do this thing. So you put one atom inside silicon, it has one electron you care about, and you ask whether the electron spin is up or down, like 0 or 1. And this is a very freaky thing. If you take a diamond and you take one carbon atom out, you make a vacancy, and you replace another one with a nitrogen atom, this creature in the middle is a qubit. And there is a company called Quantum Brilliance in Australia. This is their computer. This is it. It's like small, compact. You can buy it. It's very limited in the number of qubits it has, but you see, this is a laptop connected to a quantum computer. So the reason you have all those modalities we put here, I don't want to go into it, but you have like, what is the quantum degree of freedom we are using, how you build it, what are the pros and cons, and some of the companies which are trying to get this technology out. As you can see, each has its own pros and cons. Companies, we don't know which one eventually will prevail. Maybe there will be more than one. We don't really sure, but it's a race. Everybody is on a race. They're trying to get highly scaled computer up and running with everything that we need. These are kind of like, again, a list of all the pros and cons that we mainly care about. I think the important stuff are like, do we need to cool it to near absolute zero, like Eric mentioned, or not? Because not all of them you need to, like the one made with diamonds, you don't need to cool them. So it's like a big advantage, but it's slower or less accurate or this kind of stuff. Or maybe it's really hard to build them identical. So each has its own pros and cons, and you know, if you ask a specific company, they will say that their technology is the best and they will be the one to rule them all, and yada, yada, yada. A more visualized way for the business folks, right? You have the entire market. So we are focusing on the QPUs, on the quantum processor unit, and you see the superconducting ones, the ion trap, the neutral atom, silicon, photonics, and some other ways. But it's not just that, right? You have a computer, you need all the components to support it. So if you need to cool it, or you need the lasers, or you need connections to the QPU itself. Now we have a system. What do we do with it? We need people to develop software so we can code and run this kind of stuff. Like Classic here is an example, but you see many companies are trying to do it. Once you have a platform or a programming language that you can talk to this computer, you need to build applications for it. So Multiverse is a Spanish company. They chose to focus on finance. So they work with banks for like credit risk assessment, portfolio optimizations, all this kind of stuff. Protein Cure, they look at protein foldings for drug discoveries, cures, all this kind of stuff. And once you have all of these, you need to have someone to pay for all this pleasure. So you have the users themselves. So the main applications we will talk about more about like tomorrow, but material science, like you want to develop new materials, finance stuff. If you look at Goldman Sachs, JP Morgan, Wells Fargo, they hire quantum people. They hire PhDs with knowledge about quantum mechanics and quantum computing because they want to be able to take advantage of it. Because if I can build you a portfolio that will give just 0.1% higher return, and you invest $100 million with me, I will give you more money eventually, right? So even if it's slight improvement, they want to be the first one to have it. Life Science, Volkswagen, for example, they optimize their facilities when they want to build and assemble the car, right? They used quantum computers to define their assembly line to make it more efficient. So now they produce cars much faster than their competitors because of it. So it's a big landscape. There are a lot of players in it. They all wanted to succeed for their own benefit, but it's not just the computer. And the companies we marked with this red rectangle, these are full stack companies, meaning they do this part, but they also try to do this part, and they try to do this part, and they try to connect directly to the users. So some companies try to go like all in, some focus on specific aspect of this puzzle. But the real problem is actually the hardware, right? From everything we saw before, developing software is relatively easy. Finding applications, it's hard, but we know about applications we can use. Hardware is currently what is actually limiting us. So we can look at Rigetti. This is a superconducting qubit company. You look at the roadmap, and you see that they scaled. They started in 2018. They had 8 qubits. Took them a year to get to 16, 32, 40. And if you look carefully, you see they were connected in hexagons. We'll show you about it later on. And now they moved to squares. But getting to somewhere where you have enough capacity to do something meaningful, this is the problem. This is the challenge, getting all the way here. So the way people talk about it, now we are in the noisy intermediary something qubit. And the idea is we have qubits we can use on the computers we will use, but they are not noisy. We can't correct for all the errors and all the noise, and we don't have enough of them to do something meaningful. We believe that by 2030, some say earlier, you see like around here, we're expected to have like above 1,000 or 4,000 qubits. Then we will start to be able to have quantum advantage. But it will probably take longer until we'll have like full scale, they call it fault tolerant computer, where you can correct all the noise, all the errors, all the coherence time problems. Once we hit there, then you have like the perfect computer. But still a long way, but a lot of companies project that it will take them like 5 years to get to something meaningful, that you can actually have benefit for your business.
And I wanted to just loop back to a previous conversation we had about, you know, the probabilities and kind of cleaning up those qubits as they get noisier and noisier. That's what we're talking about with the fault tolerance, right? There are certain algorithms you need and to clean up these qubits, but they require more qubits. So you need a sufficient number of qubits before you can start using some of them for fault tolerance. So until we get to that point, right, there's certain applications we can do today. But a lot of business scale applications are going to require very long computations, and we want to make sure that it's fault tolerant throughout the entirety of it, right? So we need to get to that point where we have, 10,000, a million qubits to be able to go ahead and do these larger scale computations. In fact, we did a little bit of work recently with Microsoft. Now has a resource estimation tool on their Azure system that will take an algorithm you've developed and then project out what are the resources it would take to make this fault tolerant. And then you can see, okay, I would need a computer of this many qubits with this kind of, ability to rotate the gate set to do this in a fault tolerant way.
How connected are these systems? For example, today we're talking about IoT and we're talking about digital twins and digital threads. which requires a lot of associated, devices to be connected in,
Yes.
two-way flow of information.
That's one of my favorite topics. Absolutely.
The Volkswagen line optimization, or if you're talking about material sciences, one of the things everybody's looking for is a two-way communication, right? So how does that work with the quantum computing capabilities today?
Yeah, there's a couple of ways to talk about interconnections, right? The interconnection between classical and quantum computing, right? Because you need to eventually communicate with a classical computer and interpret that and see it on your screen. So there's a lot of work going into how do we speed that interaction up? How do we send jobs that require iteration back and forth faster, right? Batch jobbing, things like this. A lot of these companies, right? Amazon Web Services is also has a way to do batch jobs in a way that you don't have to go back in the queue for the computer every time. That was a big pain. But there's also the interconnectivity of the qubits themselves. Different systems have different interconnectivity. Not all of these qubits can interact with all of the qubits. So if you're doing a calculation that requires multiple qubits, 2 qubits, when you're programming it, you have to worry about which hardware am I going to run it on, and do those qubits actually communicate in the system I'm going to run it on. So there's some of that minutiae you have to worry about at the assembly language level when you're coding stuff. Yeah.
Right, so when we talk about like building the computer, we discussed like what are the criteria, what are the minimum requirements you need to have. We said that we have several modalities. We don't know who will prevail eventually, whether it will be just one or more. And we saw that we have like an entire ecosystem to make it work. And the main problem is the hardware, and mainly that the qubits are noisy, right? No matter how much effort we put in it, they're still losing themselves, they decohere.
All right, using quantum computers. Good stuff, right. Right, we're talking about this coherence time, right? You have to balance right, your need to isolate from the environment to essentially being able to communicate with your qubits. So you do need to eventually figure out how do I extract the data. And any way you do that has to communicate with the outside world. So you're introducing some amount of heat through that interconnectivity. People are just trying to figure out intelligent ways to limit that heat as much as possible. Right, so when you're building a computer, you have to worry about that. And also, when you program quantum computers, right, what we're going to be doing today in the workshop, you're assuming in your calculations and you're building the circuits that your qubits behave perfectly. And we call these logical qubits. Qubits don't behave perfectly, right? And so to mimic a logical qubit and behave nicely, you would need quite a few physical real-life qubits. Physical qubits, right, they do decohere, they're noisy and error-prone, so you would need quite a few of them to have an error-free calculation. So anything you do with kind of these logical qubits, just assume it's going to be a much larger circuit at the end of the day if you want to do this same kind of thing in a fault-tolerant way. Yep.
It's maybe not the perfect example, but you can think about blockchain here, for example, right? The idea of what makes blockchain powerful is the fact that we all keep a ledger of what is the state of the system, and we all need to agree on it, right? So if you have many physical qubits, and then all of them need to hold the same information, once they all agree, then you have this logical qubit. And if one qubit is off, then all the rest will say, no, no, no. You have a mistake, let's correct this mistake. We all agree that this is the right state of